Our lesson today comes from section 3.8, Explicit Formulas for Arithmetic Sequences. So you can see, knowing in 3.7 we talked about recursive equations for arithmetic sequences. We're now going to talk about the other choice. Evaluate or find the explicit formulas for arithmetic sequences, recognize the properties of these sequences, and then model situations involving arithmetic sequences. That would be real-world problems. So, getting started, remember our definition for an arithmetic sequence. It's just one way an equation can be written, a sequence can be written. A list of numbers is because the sequence continues with a constant difference. Now, we said in the previous section, and we will say again in this section, that constant difference could be an add 3, add 3, add 3 all the way through. Or it could be add a negative, make it a negative 2. So some people will say it's a constant increase or a constant decrease, but it has to be that addition or subtraction component, and it has to be the same number over and over and over again. Now, the only difference is that we have this two different types of equations that we can write. One is recursive, which we said was the two-part problem. And you had to basically do that repetition, that recurring process, use the last one to get to the next term, use that term to get to the term after that, etc., etc. Explicit, our definition was, if you remember, early on in Chapter 1, that explicit gets you there directly. So you can go and directly and find that one and only one term. In most cases, it will be faster than the recursive, so keep that in mind. But we're still working with arithmetic sequences. So as we move forward, let's look at these sequences one at a time here and decide, are they arithmetic? That's your question. Are they arithmetic? So your job is to say, well, wait a minute, start looking at them and start noticing that difference. What is it? And difference between 15 and 20 was a plus 5. Then between 20 and 25, a plus 5. And then between 25 and 30, a plus 5. So at this point, you would conclude, you have 4 terms in your sequence, you would conclude that this is, yes, an arithmetic sequence. Okay? We're not doing anything more than identifying yes or no at this point. So the next one, you start looking, I'm at negative 12. Let's see, going from negative 12 to negative 15, that's a difference of 3. And is it 3 in the positive direction or 3 in the negative direction? You should have said we were going down by 3, so subtract 3. Then here, 15 to negative 18, negative 15 to negative 18, again, is a change of 3. Then from negative 18 to negative 21, yes, it's a change of 3. So if you get that constant number over and over, then you can tell whether you have that constant difference. Third and final one, our difference from 2 to 3 was 1. Our difference from 3 to 5 is 2. Our difference from 5 to 7 is 2. So now we have to say, is that a constant difference? Just because we got 2 twice, and it seems like the 2 would be next, all of them are not the same. This guy being different causes it to be a no. And please do not assume that all sequences in this chapter, these last 2 sections in particular, will be arithmetic, because they will throw some in that are not. So look at these questions. Don't assume, or the statement, don't assume an arithmetic sequence on any of our problems. That's going to be part of your work. Look to determine whether you have an arithmetic sequence first. And then the last question, what is the least amount of terms you need to determine an arithmetic sequence? You need to make sure that there is that sequence going on and every term is that sequence. I have 4 terms up here in each. Do we need 4? Do we need 3? Do we need just 2? I think we need minimally of 3, because we have to determine, are the first 2 terms that what is the difference. So if we just had 2, we were just determining the difference. If we had 3, we could determine that the next term is that same difference if they are arithmetic. If we had a third one, it would sort of like guarantee it. So minimally, 3 terms is what we need to determine whether we have an arithmetic sequence. Next, let's take a couple of them and let's see what happens with these sequences. We should be able to write an equation from both, first determining are they arithmetic. So 5 to 11, most of you would say, is a difference of 6. 11 to 17, another difference of 6. 17 to 23, 6. We can go. So we got 6, 6, 6 all the way through. It's an arithmetic sequence. So we should be able to write any more terms. If they said, what is the 6th term, you should be able to tell me that. If they say, find the next 4 terms, you should be able to write that. We're going to be looking in a second at what it takes to find the sequence, determine and write it, and that will be in our next example. But look at this next one. Do all arithmetic sequence have to go up, which is what we're seeing here. This one goes 20 to 15. Well, most of you know that's a difference or a drop of 5. Going from 15 to 20, again, another drop of 5. So yes, this is arithmetic, and yes, this is arithmetic. The key pieces that you're going to find out we need is that constant difference. So we can call right now on this one that constant difference is a -5. Over here, that constant difference is a 6. We also are going to need what is that first term, because we can't just say we want a sequence with a constant difference of 6, because you could start with anything. So if we say our first term is 5, that's going to be a key piece on this one. And over here, our first term is 20. And then we could, with that and the constant difference, we could come up with this sequence. All right, next slide. Now, there is a pattern as we go through. So on this one, we're going to say our first term is 10. Our constant difference is a 2. So we would know that we would start with a T1, or first term, of 10. We know our second term would basically be 10, the first term, plus that constant difference. Now we know that comes out to be 12. And we keep going. The next one would be 2 of those constant differences, and 2 times 2 is 4, and 10 plus 4 is 14. And 10 times, or T sub 4, again, we start with a constant difference of 2. We have our 10, which was our first term. We have another difference, so it's 2 times 3, which is 6. 10 plus 6, 16. We have 4 constant differences of 2, which is 8. 10 plus 8 is 18. You can see the pattern as it builds. So the question is, what's it going to be when we get down to T sub 100? You should be able to tell me right now that any time we have a sequence based on what we just did here, there's our first term, there's our second term, third term, fourth term, fifth term. Do you notice a pattern? Yeah, it's going up by 2. We know that. They told us the constant difference was 2. But what else are you noticing? The way that I have it written, other than just looking at the final values of 12, 14, 16, 18. Compare it back over to these key pieces, which are your terms. They're sort of counting for you, so that we should be able to write that T sub 100 statement right now based on this pattern. Anybody notice it? Hopefully you're saying that every next term in the sequence, so T sub 2, T sub 3, T sub 4, T sub 5, has a pattern involved. And when I'm calculating T sub 2, I'm only using one of my constant differences. When I'm calculating T sub 3, I was using 2 of my constant differences. T sub 4, I used 3 of them. T sub 5, I used 4 of them. So you can say you're using one less than the counting term you're currently on. So let's go down to T100 and let's write its sequence or pattern based on this. Its first term would have started with a 10. It would have been plus. Our constant difference is still a 2. But if we go based on the pattern we observed up there, we're noticing it's 1 less constant difference. So we want to say n is our number, minus 1, n is our counter, our index, we like to say, subscript some people call it, and I put n minus 100, so let's back off on that, n minus 1, and then times that constant difference, we put a 2 right there. And so in this case, if it's n minus 1, we could even erase that and say, well, you know that value. So let's erase that idea of n minus 1, and let's put how many we would have. If it's minus 1 and we're at 100, 100 take away 1 is, and you better be saying 99. So you do 2 times 99 plus your 10, and you have the 100th term in your sequence. Now, by looking at this also, you should be able to tell me a generic, totally variable version of what an arithmetic explicit equation looks like. Let's try it. T sub n, any term in my sequence, will be calculated by taking our first term plus, we said that pattern was n being your counter of your term, minus 1 times that constant difference in your problem. So if you look at that and say, that's my generic rule, that's what I use for every term in my sequence, you can get to any term right now. You could go to the 5,000th term in this sequence and never have to list any terms other than the 5,000th. So with that information, we should be able to, as I said, write it generically. So here's that same list that we just did, finding that 100th term. And now here's that same list, looking at it, with generic variables. So again, over here, we know this was going to be 10 plus 2 times 1 less than our counter. 1 less than our counter, that has to leave us that 99. Over here in the generic version, if we know our first term is a and we know our constant difference is d, and we're still looking at, we are looking at 1 less value every time. So we get down here to t sub n, we should be able to say a plus 1 less than our current counter, n minus 1, times that constant d value that we found was our difference. That will be the formula that we call the arithmetic explicit sequence. So seeing that, let's go with it. We have that generic equation up top. We will use a sub n equals a sub 1 plus n minus 1 times that constant difference, and we will use it for different sequences. Now, the first part, let's go, of this question is, find an explicit formula for the arithmetic sequence 12, 14.5, 17, and 19.5. Meaning, we don't have just whole numbers here. We can do it with that, no problem. So double check and see that you have your terms listed. We have, you can see we have a first term, we have a second term, third, and we have a fourth term. So we have plenty of terms. Let's do that constant difference. So when we do that, 12 to 14.5 was a difference of 2.5. From our second to our third term, 14.5 to 17, also a 2.5. And from our third to our fourth term, that 2.5. So when we see we have that constant pattern, we should then be able to write a generic sequence, and then, as you can see, go on to part B. So let's come over here and say a sub n, we don't know what term we're looking for, is going to be equal to our first term in our sequence, a sub 1. In this sequence, it's a 12, plus n minus 1 standing for how many terms are we going to actually calculate, and it's going to be one less of them times that constant difference, and we found that constant difference to be 2.5. Now, some people really do not like that 2.5 at the end of the parenthesis. You could put it in front, and it would read a sub n equals 12 plus 2.5 times that n minus 1. Still works the same way, still will work out calculating it the same way. So here we go. We want the 25th term in our sequence. So we're going to start a sub 25 equals, what was our first term? Well, our first term was 12 plus our constant difference was 2.5 times that n value, where our n value is 25, so 25 minus 1 is 24. You do the math, get out your calculator, and we need 2.5 times 24, and then add 12 to that, and we should have our final answer of the 25th term in this sequence came out to be 72. That's all there is to it. So, looking back, let's try one more. It's a real-world application. Take a look. The first row in the auditorium has 15 seats. Each subsequent row has 3 more seats than the row in front of it. If the last row has 78 seats, how many rows are there in the auditorium? So right away you're looking at this one and saying, okay, well let's simplify it. Let's write down what we have. So the first row in the auditorium has 15 seats. That's like, let's call it r sub 1. Our first term is 15, because that's how many seats are in that row. Each subsequent row has 3 more seats. So that would be that constant difference. If the last row has 78 seats, now right now we're thinking last row. We don't know what last means. So r sub n equals, and it has 78 seats in it. How many rows are there in the auditorium? So we should be able to figure that out based on using our arithmetic explicit formula. So let's write that down. This time the only difference is we're going to use the r values. So r sub n has to equal our first term plus n minus 1 times that constant difference. Now let's put in the values we know. R sub n, the number of seats in that last row, is 78. Our first term is 15. Our n value, which is the counter, the row we're on, is what we do not know. So we've got to leave that as n. And then d, our constant difference, is 3. So look at this one, where previously we knew n and we were solving for r sub n. This time they threw a little hook at us and they said, you know, if you really look at this, you have 1, 2, 3, 4 variables. And the key is you need 3 of the 4, and you can solve any of the other missing pieces. So right now we do have 3 of them. We have r sub 1, we have d, and we have r sub n. So what we're missing is n, and n stands for what row we are in. So that's what we're solving for. So we are really looking at a algebraic equation that can be solved. So let's go ahead and do that. We've got 78 here and 15, which are regular numbers. Just leave them alone for right now. Let's go ahead and distribute. 3 times n, 3n, 3 take away 1, or 3 times negative 1 is negative 3. Let's combine like terms on the right-hand side. 15 take away 3 is 12. We still have our 3n over there. Now we can start looking and say, well, wait a minute, we got 78 over there. Let's move this 12 over with a subtract 12. When we do that, you can see we get 66 equals 3n. You know what to do from there. Divide by 3, and n equals 22. So we're able to answer the question, how many rows are there in the auditorium? There would be 22 rows in this auditorium. So there's a real-world example of how we're going to solve these. arithmetic explicit equations, you should be good to go to try the regular formula ones as well as the real world examples.